Yeah, Assalamualaikum warahmatullahi wabarakatuh. So we continue with our chapter number 2, structure of biomolecule. So revision of organic chemistry. So week number 3. Okay, week number 1, lecture number 3. Okay, so every molecule have a special distribution. So every atom cannot uh, be at the same spot, and it need to be at the certain angle, okay, and a certain length. Okay, so as you can see here, okay, so we have this length. What is the length of this uh, between N and this C, and let's say N and H. Okay, so we have a certain length, and it also has a certain angle. Okay, so it depends. So for that, it will make this uh, molecule. Okay, so we have this type of molecule, or this type of angle, uh, this type of molecule with this type of angle and the length between each atom. Okay, so what we can say is that directional properties of chemical bond are related to special structure of the biomolecule. Okay, so this one C, between N and H, this is the length, and with this angle and length, so it will determine the biomolecule function. Okay, so let's say if this molecule is in a different position, or in different conformation, so it will not be active. Okay, it will be passive. So when it goes to the certain configuration, so then it will be active. Okay, so this special structure of a molecule also depend on the special distribution of electronic state of the constituent atom. Okay, so C, let's say carbon have it as orbital, nitrogen has its orbital, on all the atom has the orbital. So we go to the special distribution depend on this atomic orbital. Okay, so as we know from our you can see from your physics or your chemistry. Okay, so we have the s orbital and p orbital, and we also have d orbital and l orbital. Okay, so today we only see this s orbital and p orbital. Okay, so these are the electron cloud, and this is also the property of finding the electron cloud in x axis, y axis, and z axis. Okay, so when the electron in these two orbital s and p meet, okay, so it will produce for this one, when one s orbital plus 3 p orbital, let's say we have 2s n equal to 2, so we have 1s, 2s and 2p. Okay, so for that, when this do the hybridization, so we are going to have this 3 sp3 orbital. Okay, so we have this sp3, 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 and sp3. Okay, so when this one plus this 3, so we are producing this 3 orbital. Okay, and then if 1s orbital plus 2p orbital, so we are going to have sp2 hybridization. Okay, so we can share the electron with this sp21, sp22, and sp23, and 1p orbital. Okay, so meaning that we have 3 sp sp2 orbital and one p orbital. And we can see that this what we mean about this direction of the molecule. Okay, so here we have 120 degree of between sp2 and another sp2 orbital. For sp hybridization, so we have one sp orbital plus one p orbital, so we are going to get two sp. So this one sp and one sp, and we have p orbital and this p orbital. Okay, so we have, and here you can see that the angle is 180 between sp and another sp orbital. Okay, so here these are the example. So we have the carbon atom has 4 electrons in the outer shell that are organized into 4 sp3 hybrid orbital. Okay, so we see here we have the carbon have 4 electrons, 1 2 3 4. Okay, we have 2s and 2p, the second level. Okay, so here we can share this one electron goes to this one, and you can see that it can be produced into this 4 sp3 hybrid orbital. Okay, so meaning that there is a one electron not missing, the can put here, and one electron can be shared here, one electron can be shared here, and one electron be shared here. So here we see C, so H share the electron with this sp3 orbital, so we can have this methane. Okay. Okay, and for the nitrogen, so you can see that the nitrogen has 5 electrons. So in 4 sp3 hybridized orbital, so it can only make 3 connection, or only 3 atoms can share the electron with the nitrogen, because one is already full, so we only can put one electron here, one electron here, and one electron here more. Okay, and here we can see that the repulsion between the lone pair electron and the electron in the bonding orbital decrease the H and H bond angle from 109.5 to 107.3 degree angle. Okay, so we can see here this, let's say this is 109, this is 107 and 109. So it define the direction of that molecule. In this case is N and H. Okay, so the degree of deviation, okay, the direction of the molecule depend on this degree of deviation. So even though we say that this using this electron dot structure and line bond calculate and revise this structure CHH, but in real life this H, and in this H we have a different angle. Okay, so this also a different angle and a different length. Okay, this one different length, this also different length. Okay, so these are methane, ammonia, water, and methanol. Okay, so these are some molecule. Okay, so here you can see that we have this, and we replace all some H with methyl CH3. So this 8 become 18. So you can see that the length between C and C carbon and C carbon 153 picometer, and the angle between this C line and H become 111.2 degree. Okay, so we have the direction of the atom in the molecule. Okay, and again this one C and C, these are double bond. Okay, so you can see that here is only one bond. Okay, so we have 111.2. Here double bond, so become 121.3 degree, and the length, or the length between C and C is 134 pico meter. Okay, so again this one with CH3 methyl amine. So you can see here we have 107.1 degrees and 110.3 degree. Okay, so we can see that here we are saying that before this the nitrogen is 109, 107 to 109, but here we can become 110.3 degree. Okay, and here for the methanol CH3, okay, so we have this 108.5 degree from this between H and CH3. Okay, so these are the direction of the molecule. Okay, and for a long biomolecule, so we have also the conformation state. So here we can see that these are the group R1, group R1, and group R2, and this also group R1. And here we can see that when it's Gaussian, group R2 position is at this point, compared to the trans, the group R2 is at this point. Okay, and we can see here the Gaussian and trans. So we will plot the potential energy and the rotation angle. So if these are rotating, this we rotate between this bond C and C. Okay, so here with -5, 0, and -20 kilojoule per mole. So you can see here the trans, in this case the trans is much lower energy from the Gaussian. Okay, so the Gaussian keep trying to moving and try to find in or become a trans position. Okay, try to get to this point, that is a trans molecule. Okay, so the example here. Okay, so the example is butane. Okay, the butane Gaussian. So you can see here CH3 and CH3 from, if we see it from the front, okay, or C axis. Okay, so it will rotate 60 degree and taking the 4 kilojoule per mole. Okay, become CH3 trans. Okay, so this one is 3.8 kilojoule per mole, 19 kilojoule per mole. So this is its probable position or direction of this molecule. Okay, okay, so these are energy more than average thermal energy. Okay, 90 kilojoule per mole. Okay, and the average thermal energy is about 20 kilojoule per mole. Okay, so because of this direction, okay, trying to get to the most lowest free Gibbs energy. Okay, so we have a conformation or configuration. Okay, so here you can see that if we have let's say these two are C5, okay, carbon 5, we have 5 carbon. So it can be in this shape, or in this shape, or in any other shape, but these are the most known. Okay, so envelope and or the half chair. Okay, so we have this. You can see that the angle between this C and this C, the angle of this C and this C, the angle of this C and this C will be different. Okay, so we determine the shape, or the shape of the molecule. Okay, and this one for 6 carbon. Okay, so we can have the chair, the twist, the boat for uh, direction, or not direction, the configuration. Okay, so we have this. Here we can see that the degree 0 degree, 0 degree, 50 plus 51, 51 minus 51 plus 51 degree. Okay, so these are the example. Again, the example. So these are for the 6 carbon atom. Okay, so we can see these are the strain, torsional strain, and these are the strain. Okay, so it tried to uh, have a lowest free give energy, so that uh, the molecule will be stable. Okay, so here in this case, the twist both cyclohexane. Okay, so 20 kJ per mole per strain. Okay, the strain. So next we have again the isomer. Okay, so the isomer is just the same various chemical form of chemical molecule that have the same summary formula but require bond breaking and resolution. Okay, that is called isomer. So the example is pentane C5H2. Okay, so here we can see that 1, 2, 3, 4, 5 carbon, and this one we have 4 bond, and this one it have in this C atom, so we have 3 bond. Okay, 1, 2 bond. So this break one carbon attached to another carbon, and this also in all the center carbon share the electron with another carbon. Okay, so become this molecule. Okay, so here these are the table of this important bond CC. So these are all the important bond in this biomolecule. CC, C double bond, C N double bond, C N, C double bond N, CO, C oxygen, C double bond oxygen, CS sulfur, OH, NH, SH, CH, and HH. Okay, and this you can see that this the bond distance, and you can see that for this one, for CH and HH, so you can see that HH is near, CH is far away, 0.109, but the energy need to break this bond. So for CH 410 and for HH 430. Okay, so meaning that this bond is greater than this bond. Okay, maknanya susah lagi nak break this bond daripada this bond. Okay, and next we have this. Again, these are just revision of organic chemistry. So we have enantiomer and chirality. So enantiomers is a simple mirror image of their counterpart. Okay, so we put the molecule near the mirror and see whether it's a left hand or right hand, so you can see the difference. Okay, and for this one is a chiral. Okay, superimpose. Okay, you can see that this hydrogen and this hydrogen is superimposed, and but here this fluorine, okay, in this one, so this fluorine cannot be imposed to this mirror image, this fluorine, so these are the chiral. And next is the D and L sugar. Okay, so dextro D for dextro rotary, and L is for levo rotary. Okay, so this example: L glyceraldehyde, L glucose, D glucose. Okay, so what we can say about this D and L configuration, or D and L direction, okay, the molecule direction, taking direction, is that all biologically active monosaccharide are D types, okay, meaning that if this monosaccharide and it is D type, so it will be active. Okay, but if in L type, so it will be passive. Okay, and all biologically active amino acids are L type, so meaning that when this L type, so it will be active. If in D type, it will be inactive, meaning that uh, in the reaction or doing the association with another type of molecule. Okay, and here also we have the sigma bond and pi bond. Okay, sigma bond is covalent bond formed by orbital overlapping end to end with electron density concentrated between the nuclei of the bonding atom. Okay, so these are sigma bond and these are the pi bond. Okay, so we have these two bond. Okay, so and the sigma bond is much harder to break rather than this pi bond. Okay, so meaning that here we can see that, or we can say that we can break this bond first rather than we, we can break this bond. Okay, so we can break this bond, but we need a lot more energy to break this bond. And also meaning that this, let's say, H can be substitute with other atom. Okay, let's say bromine. Okay, so here these are example. These are unsaturated bond. Okay, so these are propane, C double bond plus HBr, so we have this replacing or breaking this one bond, the pi bond, and making a new bond with the bromine. Okay, and these are type of double bond, CC, CN, CO, imine formaldehyde. And again, we have this cis and trans double bond example. Okay, so double bond, so it can produce a cis or trans configuration. Okay, so here 1, 2, 3, 1, 2, 3. So this R group is at the above, and this R group is located below this main molecule. Okay, and the pi bond and delocalization. Okay, so here pi bond can move freely or the electron in the pi bond can move freely. So here we can see that these are sigma bond and pi bond. These are pi bond, pi bond. So this electron can move freely uh, between this C atom, C atom, C atom, C atom, and this also. Uh, you can see in this position or in this position. So it can the electron can move freely in this pi bond. Okay, and this also the electron can be here and or can be here. Okay, so the electron can move freely from this oxygen to this oxygen atom, and this 50%, 50%. Okay, so this electron can be here or can be here. Okay, so it can move from this electron, this oxygen to this oxygen. Okay, the last one again. So here, electron here, electron here, electron here, electron here. Okay, O O double bond, double bond. So we can have the electron can move freely between this oxygen attached to the phosphorus. Okay, and this also oxygen and H the nitrogen. Okay, so that's all for this lecture.